So we're going to spend the next handful of slides exploring the black pixel assumption. I just threw these maps up because I have a couple of case studies and wanted to make sure everybody was just familiar with the body of water that I'll be spending some time on. Chesapeake Bay, where I'm from here. Maine is kind of up there. And the Sargasso Sea, Bermuda. All right, so the black pixel assumption. Are remote sensing reflectances in the NIR really black? Has anybody had a chance to look at radiometric data that you might have taken off the dock or on the boat yesterday? And have you looked at the NIR by any chance? Not yet? Okay. Here's a remote sensing reflectance curve from the Sargasso Sea. This zooms in on the near infrared reflectances. You can see it's pretty close to zero. This would tell me that the assumption is pretty good. Should say Chesapeake Bay. Nevertheless, these data were collected in the Chesapeake Bay. You can see a substantial difference in the spectral shape, but there's some signal down here all of a sudden. And it might look insignificant, but it's not. So for Chesapeake Bay, if we just assume that the black pixel assumption is correct and assume that this is insignificant, that is negligible, what is the impact of that? So I have a bunch of panels that look a lot like this, so I'm going to walk you through it. This is almost 10 years of Motifs data. All the blue lines will be Motifs data. This is, for this entire time series, histogram of RS at 412, RS at 443, derived chlorophyll, and angstrom. The gray shaded regions behind it are field data that I had available. These are monthly time series, so each point in here, every bend in the curve is a monthly average. These are field data with the cloud behind it being the standard deviation again. So what you're looking at here is that in a body of water where the signal in the near infrared really isn't zero, but you assume it is in total processing, the end result is values that fall below zero. This vertical line shows you where zero is. You can see that again here. And just so you know what the derived products look like, totally out of bed with what we're actually seeing in the field. Okay? So this would argue to me that while it might work, in some places, even a negligible signal, this assumption fails. So, seeing this, would you expect that it would fail in the Damariscotta River estuary? Okay, so we need to account for this. How do we do that? Well, a lot of smart people have spent a lot of time thinking about this problem. Many approaches exist. I will step quickly through a lot of them. But they fall into a couple of generic flavors, many of which require field data. First is that you can just effectively say, I know what the signal in the near infrared is, and I have a pretty good idea what the aerosol is, so I don't need your atmospheric correction. I'm just going to plug them in, plug those numbers in. The second one is, well, if this assumption fails in the near infrared, and I have a sensor like Motifs, which has shortwave infrared, maybe the assumption holds up if I go deeper into the electromagnetic spectrum. Third is, well, I'll just solve the atmosphere and the ocean at the same time. Instead of doing this, I'll solve the atmosphere problem first and then go to the ocean problem. It's a computationally expensive procedure, but you know, we're heading back that way because computers are better. And then the last one is, well, we know it's non-zero, but why don't we use a bio-optical model to correct for it? And so instead of making the assumption that it's zero, we're going to calculate some BBs and some A's, and then we're going to take a guess at what the signal is. We're going to remove it. We're going to force it to be zero, and then move on. And there are a couple of different flavors of how that has proceeded with time too. So the terms in green are the ones that I used for my case study. I'm sorry, the references in green are the ones I used for my case study. So let's start at the top. And this is a popular and very clever way of proceeding. It is fixing the aerosol and water contributions. This is Kevin Ruddick's model. He calls it MUM. So I ran it twice. And you'll see that there are two different curves. One is blue. That is just the default configuration for where the model was developed. Not necessarily something that should ever be applied to Chesapeake Bay. And then I took a wag at trying to take the data I had and come up with some terms. In the defense of this model, I probably spent an hour on it, so it wasn't one of those robust spending 6 months trying to tune it. I could do a better job at some point. But the punchline that I want you to take home is this kind of approach is very powerful in the sense that you get much, much closer to picking the right aerosol model so that you don't suffer from negative values. Your derived algorithms tend to approach what you're actually seeing there in both the time series and the distributions. Angstroms may be a little off, but that's okay. The advantages of this kind of approach is when you configure it accurately, it leads to accurate aerosol retrievals and remote sensing reflectance retrievals. That you could implement this a couple of different ways. You can put in fixed values like I did, but conceptually, you could use climatologies if you had enough information so that you knew what the temporal signal might be for your neck of the woods. Or perhaps you could just search nearby pixels where you know the assumption for black pixel is valid, calculate it there, and then translate that to the pixels where you know the assumption is no longer valid. The final advantage is that this method is portable to all different kinds of sensors. Everything that is flown, you can use this method. The disadvantages are no configuration is valid everywhere at all times. It requires local knowledge, which you may or may not have. And quite frankly, its implementation can be complicated in an operational environment where you're passing petabytes of data through a system at all times. Any questions? So the second one is the use of shortwave infrared bands only. So this is saying, okay, I don't believe the black pixel assumption in the near infrared. I'm going to go to the shortwave infrared, and then I'm going to proceed exactly as I did before. This, in theory, is a very, very good idea. So in this case, what did I do? Why do I have two colors? Turbine only, SOAR turbine only. Oh, okay. Rather than looking at every single pixel in Chesapeake Bay, I only focused on those pixels that a flag indicated were turbid so that I was getting away from those other pixels where shortwave infrared wouldn't offer any advantage. Yeah, that's what I meant there. So, okay, so in this case, the blue line is a bio-optical model. So I'm sorry, this is not. Pay only attention to the red line. I'm sorry, I'm fumbling here a little bit. This was for a different purpose. My apologies. So look at the red line where we're doing SOAR bands. Okay? And you'll notice again that you're getting nice time series of positive values. Your chlorophyll is doing pretty well. The first thing that you're going to notice, though, is that it's kind of a squish distribution here. And this isn't necessarily a problem for a sensor designed to do this. The problem is that the only sensor we have now that has shortwave infrared bands designed specifically for doing other things than other ocean color is Motifs. And the signal to noise on these bands is so low that you're getting a lot of variability in your shortwave infrared radiances. And so what you're seeing here, this flattening of the curve, is simply the squishing and the spreading of the total signal based on noise introduced by these channels not being designed for this application. So the reason I included these blue curves was to show that if you do this correction another way, and you can see that on average, the shortwave infrared version is giving you the same answer on average. The medians are pretty much the same. The problem is that the signal-to-noise issues that we're dealing with have just squished the distribution of it. So in current practice, it is not an operation. It is not a fully desirable solution. Next generations of sensors are being designed in a way so that the signal-to-noise problem is alleviated. Yes?
Can they use this on veers?
They can use it on veers, yeah.
Is it a better square band?
I don't think so. I mean, it might be a small step better, but it is not. Yeah. I mean, you're talking about, whilst theoretical papers usually talk about order of 100 to 300 SNR, and most of these, since they're designed for cloud and aerosol applications, can tolerate much, much lower, so you're getting the 25s to 50s practice. The purpose of the slide is just to point out that there are some applications that you'll find in the literature which are clever enough to say, I recognize that the SWIR does not work in all places at all times, so I will combine it with the NIR, and the clever part is that they put a little model on the inside that tries to identify whether the pixel is turbid or not. So if it goes one way on that threshold, it says I'm going to use the SWIR application. If it goes another way on that threshold, it'll say, well, I'll just use standard operational processing. And when you combine the two, you actually get nice results here. The other reason I included it is to applaud that model, but also to say that it has evolved over time, and since there is some empiricism and some subjectivity in pre-assigning whether a pixel is turbid or not, you can see differences in your time series just based on your choice of whether those pixels are turbid or not. All right. So the advantage of this is that the black pixel assumption is largely satisfied in the SWIR region of the spectrum. Now, there are a lot of other papers that have come out since then and have suggested that there are inland lakes and there are bodies of water where this still fails, but it gets you moving in the right direction. It is very straightforward to put into processing because it operates exactly the same as what we're already doing, but the disadvantage is that not all heritage instruments have SWIR channels. And so if you're trying to create a time series from, say, CWIFS, which runs from 1997 to 2010, and you put Maris in there, and now you want to add Motifs, which is 2002 to present, you're mixing your atmospheric correction if you don't do it consistently all the way through. So you might choose to not do this for your climate data record, your long-term time series, because not all satellites can support it. And you can see the differences in doing it and not applying it and not applying it, and that might introduce a trend into your long-term series that you don't want there. I already mentioned this. What I didn't mention is that it is very difficult to calibrate the SWIR bands. If the ocean is black there, then your calibration source is difficult to measure. And as you saw in the last slide, switching between the two can be complicated. So the last one I'm going to talk about is the bio-optical model. And so what we're doing here is we're using field data and some empirical algorithms to say we can take a pretty decent guess at what remote sensing reflectance in the NIR is. And I won't belabor this plot anymore, but as you can see, like the other ones, it moves everything in the right direction, and it does a pretty good job of fixing the problem of the black pixel assumption. Yeah?
So,
I'm going to go through it in detail. The way it operates, is that what you were going to ask? Yep, I'll come up to it. Advantages available for all past, present, and future missions. It's pretty easy to implement. The disadvantage, of course, is that anytime you're using a model, it doesn't necessarily work everywhere at all times. So let's step through this bio-optical model. And the reason I'm doing this again is you collect field data. You're going to get NASA funding. You're going to give data to CBAS. We're going to use it to refine this model. If you're not measuring BB really, really accurately, this all breaks down. So please, please, please measure BB very, very accurately. So, all right, so it's an iterative process. We take a guess. that at 670 nanometers. So for the first step in the iteration, we go with the bioptical assumption. We go with the black pixel assumption, and we come up with a first guess at RRS at 670. I mean, doing this for Motifs, it would be CWIF, so it would be 667 in Motifs land. Then we take a guess at what total absorption at 670 would be. In this case, we're talking about contribution from water, and then the contribution for all the particles and dissolved material in there as well. So we know this, but we don't know this, so we have to model it. So this is the first modeling step in this process. And we do it very, very simply. In this first iteration, we take a guess at chlorophyll. And then using a bunch of field data, we relate this to chlorophyll. And this is the relationship we get. Notice it's log-log. Now you may be thinking intuitively to yourself, well, that's not the best relationship in the world, and good grief, I can't trust my first chlorophyll estimate because I already know my atmospheric correction's imperfect, and chlorophyll doesn't totally represent all particles and all dissolved material in the water, particularly in the parts of the world where this assumption fails. The reason that doesn't really matter is, look in log scale here. This line indicates 0.1 inverse meters. The contribution by water at this wavelength is 0.44 inverse meters. So water is totally dominating the signal. It's just getting nudged a little by this model. And reviewers like to see that you're thinking through all of this. So we have a guess at this, we have a guess at this, and so we can now invert this equation to come up with a guess at backscattering at 670, okay? And you've seen this expression probably a few times by now. This term comes from Morel 2002, calculated again using chlorophyll and some lookup tables that take into account solar and sensor geometries. The empiricism continues. We now take a guess at backscattering spectral slope using the ratio of our first guess of 443 to 555 in the model of Zhongping Li from 2002. And this is the expression that he has put together. This is a preliminary version from 1999 that shows how the ratio of these two relates to spectral slope. And you can see a fair amount of scatter here. So again, improved measurements from folks like yourselves will improve our ability to do this. Now that we have backscattering spectral slope, we can estimate backscattering at 765 from backscattering at 667, following this expression, which you have also seen before. Yeah?
Going back to the Morel 2002,
yep.
What is the G function?
It comes from this paper, sorry. It's F over Q. Yeah. I'm sorry, is everybody clear on that point? I was not entirely sure the form of this expression that you had been using in the class. I simplified it ridiculously here. Sorry, Kyle?
It was F over Q.
It was, okay, this is F over Q. Then we can reconstruct remote sensing reflectance at 765 using F over Q at that band, extrapolating Morel, our modeled backscattering at 765 and water absorption at 765. The reason we don't nudge this like we did for 670 is water absorption at 765 is 2.9 inverse meters. It's a huge, strong signal. Not nudging it in one way or the other is not going to be important. And then this process iterates. So now we have an RS at 765 that we can subtract from what the satellite has measured. And then we can repeat the atmospheric correction process and this process inside of it until this value stops changing, which usually takes 3 to 4 iterations, okay? So just drink that in and look at all of the empiricism in this model, all based on field data, but it works pretty well. This is to give you a sense of where it's applied. So it's not applied anywhere where chlorophyll is less than 0.3. Those are the gray regions. It's a weighted application where, I'm sorry, array. Oh, in the white is where chlorophyll is greater than 0.3. It's a weighted application between the range of 0.3 and 0.7, and then it's fully applied whenever chlorophyll is greater than 0.7. So there you have it. So now we have perfect water leaving radiance. The only couple of things left to get to perfect remote sensing reflectance are this term and this term. So I don't think I'm going to go too deeply into estimating F over Q. Ken, I believe, already talked about this, and I'm sure Kurt has brought it up a little bit. Running through the cartoon is just, here's your in situ target, here's your sun, here's whatever's in the water, and that stuff can all move with time between when you make your in situ measurement, when you make your satellite measurement, the sun position has changed, the water column has changed. We want to adjust that with the purpose of you, in a validation exercise, you would want the remote sensing reflectance measured by the satellite to be representative of the remote sensing reflectance that you measured when you were out in the field. And if you don't make this kind of adjustment, you're really not in an apples to apples position where you're normalizing the sun to a common position and the water column to, common conditions. So this takes care of accounting for the sun's change of position in the sky, which is important because of the path length through the atmosphere and all of the other atmospheric correction problems that we have, transmission of light through the air-sea interface, angular features of the in-water volume scattering functions. I'm sure you've already discussed this paper in practice. The equations are there. Does anybody want to spend any extra time on this, or has this been satisfactorily covered by now? Okay. All right, so the last correction term is kind of like this polarization term. If you do a really, really good job in the lab ahead of time and you're really, really well thought out, you can avoid it. Motifs doesn't really need this correction. CWIFS does. This is a correction for spectral band passes. So an instrument like CWIFS is a filter radiometer, which means to get a signal at, say, 443 nanometers, you put a filter on front so that the light passing through the detector really is just 443 nanometers and you get everything else out there. But unless there are practical implementations why it's never just one wavelength, it always has to be a bunch of wavelengths because it just has to be that's the way filters work. But if the filter is not carefully designed, you can get contributions from other parts of the spectrum. And so this is CWIFS spectral response for 550 nanometers, 555 nanometers. Now, if you look at the full spectral response from 400 to 1 micron, you can see its peak here. This is the signal we want to let through, but you're getting light from blue and the red. So the satellite filter here zoomed in to this region from roughly 450 to 650 nanometers. You can see that there are contributions on the order of 0.1% here, 0.1% there, but these are wide leaks. And so cumulatively, they all add up, which means 555 measured by CWIFS is not just a signal at 555, it's a contribution of whatever blue light and red light also happens to be available. Now, in principle, why would you care? Well, think of it this way. When you're developing your algorithms, or at least in the era where this was important, when you weren't using hyperspectral instruments, you were using filters on your in-water radiometers that had generally constrained rectangular band passes for the most part. So you're out in the field and you're trying to validate this, making measurements, or you're using those measurements to develop algorithms. Well, what you're seeing in the field is represented by this this gray cone. What the satellite is actually seeing is much, much different. And so you need to apply a correction for this. Otherwise, you're introducing uncertainty in your validation and your algorithm data relative to what the satellite is actually seeing. And so we do our best to correct for it. And the way it is done is through the use of a Clearwater model, Morea terrena, which is driven entirely by chlorophyll. This could be developed 100 different ways in a modern in a modern world. It could be done using hydrolate, but this is how it was done previously. So what you're seeing here are remote sensing reflectances for a variety of different chlorophyll values. Okay, the colors just represent different chlorophyll values. All right, this isn't complicated, but it's not straightforward to explain, so let me know if I'm not being clear. So for every satellite band we care about, and for each chlorophyll value in this table that we've created, we calculate a 10 nanometer mean RRS to represent the in situ data. The 10 nanometers to represent that filter applied on a filter radiometer that you would put in the field. And then we calculate the full spectral response RRS too. So in that case, for every wavelength, for every step in that chlorophyll table, we're calculating the signal from this, and we're calculating the signal taking the full spectral response into account. All right? And then we take the ratio of the two. So in this case, on this plot for this particular value, the red dot indicates the 10 nanometer mean RRS. The black dot indicates the full spectral response RRS. Represented on this axis, you can tell they're not much different, but the ratio of the two is roughly 0.95. So that's a 5% difference in what you would measure by using a satellite and measure in the field if you were looking at exactly the same water at exactly the same time. And then we perform this over and over for all of the different chlorophyll steps. And this blue curve is the ratio of those two for that full dynamic range of chlorophyll. The dotted line just indicates 1. So you can see not only is it not 1, but it changes as a function of what's in the water. And so in practice, let's see, we have the ratio. For every band, we now take this blue line, this blue line, the ratio, and we regress it against RRS full band 490 and RRS 555 full band. So if we've gone through this whole atmospheric correction process and you come up with a remote sensing reflectance at the sea surface, it's still full band. And this is the last correction step. So what we're trying to do here is to take the ratio of two things that we have, having gone all the way through this process, and then come up with where on this curve are we. And the reason we do it in this ratio space is that we don't know chlorophyll yet. We don't want to take a guess. So the final correction factor is a polynomial expression that's run through all of the dots here. Is this kind of clear?
No. Okay, so go back to the previous slide.
Yep.
We would have a separate blue curve here of the ratios for every different band, because the different bands are affected.
Yep.
Like different filters, different out of band response.
Yeah, I don't have those.
So have a blue curve like that for every band.
Right.
Then, what I didn't understand, and that's a function of chlorophyll.
Yes.
So when you go to the next view graph now, the 490,
Yep.
are you saying that to correct the 490 band, we'll compute this function for 490 to 455?
No.
I'm lost. It's like,
Yeah.
how would I take that next view graph and correct my 412 band?
Okay. So we can create this model as a function of chlorophyll, so as a proxy for what's in the water, right? And we could create this, and everything makes sense up to here, right?
Right.
Okay. The problem that we have is in the satellite paradigm is we don't have this value. So we don't want to use a chlorophyll to come up with the correction factor. So we have to use something that we do have. Unfortunately, we can't make this kind of series of curves using something that we do have. In a perfect world, I would make this, and instead of using chlorophyll here, I would just use the ratio of 490 to 555 or something like that. But there's a disconnect between getting to the, and maybe this can be revisited again using Hydrolate or a better model than the Morel one, but since there isn't a clean relationship perhaps where you could generate your lookup tables used in this using just 2 wavelengths. We do it using chlorophyll, but now we can't use chlorophyll because we don't have that from the satellite yet. So really all we're doing is using this band ratio as a transfer function to get this blue curve into a ratio that we actually trust. I didn't explain that any better, did I?
So go to the next view grid.
Yeah.
Everywhere else you need an iterative process.
All right.
Yeah, we don't do an iterative
It
process.
doesn't converge.
If we could do, if we could, would do this at the top of the atmosphere if we could.
Yeah, but could have iterated, assuming with the RRS with the R's that are not corrected for other
Make it so.
chlorophyll, guess a chlorophyll,
Yeah.
do these corrections, and see how it affects the next chlorophyll. Maybe it doesn't converge, and that's the reason why you don't do it.
Make it happen, man. There are 1,000 different better ways to do this. This is 15 years old. It's just what we're still using.
Okay, so here's my question.
Yeah.
We've now regressed, we have the ratio at 555, and we have this 490 to 555.
Yep.
I need to correct my 412 band.
Yep.
What number do I use there?
You do this regression for every, so you've calculated this blue line for every single band.
Right.
So you have it for 412, 443, blah, blah, blah. You then do this step for every single band as well. I'm only showing it at 555.
Okay.
So now you have a suite of these.
So this is the curve that I used to correct the 490 band.
This is the curve that you use to correct 555.
Okay.
So there are, for CWIFs, there are 5 others of these that have the same x-axis, but the relationship then is R443, which would be a different curve, R412, the ratio of 412 for a different curve. So you repeat this for every band. And so now what you have is a,
Discuss it offline.
yeah. But the bottom line is that you can represent this ratio at every single wavelength using just this ratio of 490 to 555. I think this is probably me not explaining it well more
The
than,
upshot is, you're talking about 2 to 4% error.
yeah. And that's,
Yeah.
this would be for CWIS at 443, where there's not a lot of light leak, and you can see the correction is somewhere between 2 plus or minus 2%. But in 555, the correction actually boils down to, at very clear water, to be about 7% for band 5 on CWIFs. So. Okay. Do you want to, what's the best way to proceed now? If you're confused, probably a lot of people are confused.
Well, you know, like I say, we don't want to bog down
Yeah.
with explaining this to
Yeah.
me,
But it's important to understand that,
Yeah.
I mean, I think the bottom line is that when you have a radiometer that you're ground truthing with, and your radiometer has a forward path max of 10 nanometers, you understand what that instrument response is, but understand that the sunlight has these out of band, and I would suggest that some of the filter instruments that we have also have out of band
Yeah.
that we're not correcting for, that we should be doing
Right.
the same correction that you're doing on the sunlight. And so it depends on how you're measuring the radiometric light field, whether you're measuring it by allowing light to pass through a filter or how you're gating that light field, and it makes a difference whether
Right.
you're in the water or in sunlight. And so you're right.
Yeah, it goes back to what I said when I was doing
Exactly.
radiometric instruments, is when you get
put a
an
filter
instrument
in.
that's a multi-channel with 10 nanometer bands, and you check the out-of-band response to it. And the same thing when you have a spectrometer or hyperspectral, that you're doing the straight line correction.
Also, you said that Motifs didn't need this, but when I downloaded the Motifs spectral response curves from the website and I integrated, you know, I could take like
Yeah.
a
I don't think I have a
lambda
Motif.
minus 4th Rayleigh spectrum the Motifs out of band numbers were on order 10%, 5-10% as well. So it would seem to me that it does need.
It is applied. I only said that to indicate Motifs looks more like this, where it's 1 or 2%, whereas there are bands on CWIFs that have the 7 or 8% correction. And really, this is more of a shock and awe. The purpose of putting this in, other than to make Colin's point, was also the shock and awe of we're using those Clearwater models to effectively impart a 7% correction on the final RRSs for use as input into the algorithms and in our validation activities.
And you're doing this correction to the RRS of the surface.
Yes.
Water line versus curve. You got to separate those two things. In both Motifs, CWIFs, everybody did full band calculations when they did the Rayleigh correction.
Right.
Yes, yes.
How the atmosphere. So that part that you integrated there is already taken care of, not a problem.
Right.
It's this additional thing that when you get to the bottom that CWIFs had more of a problem than Motifs had.
So Ken, you're saying that, well, like in the old Gordon paper where he talks about this out-of-band response, and he says, oh, well, you know, if it's lambda to the -4th, you're going to get one answer, and if it's something else, you get another answer, because the out-of-band response depends on the wavelength dependence of the signal you're looking at.
Yep.
And now you're saying that the Rayleigh part is built in somewhere.
In the atmospheric correction process, they've taken account of full band response.
So the Rayleigh tables are generated using full.
That would be built into the Rayleigh.
Correct.
paper.
Yes.
Okay.
Full spectral responses in the yeah.
Papers I read.
Yeah.
Okay, so now I understand why you're only doing this to
At the bottom,
RRS,
yeah.
Whereas Gordon's paper says separately, oh, we do this for Rayleigh part, we do this part for aerosol, you know, whatever. So that now makes sense.
Yeah. Okay. We'll talk about the other stuff afterwards. You had a question?
Maybe this is something I missed or just forgot, but why are we doing the ratio between 490 and 555?
Oh, sure. That just dates back to the legacy of when CWIS was first launched. We didn't trust 412 and 443 all of that much. You know, those were the hardest ones to deal with in the atmospheric correction process. So those were just two bands that were as reliable as what we had. So.
I think, if I understand this correctly,
Yeah.
if you go back to the plat regress, the full band RRS, if you just, the next slide, if you just flip that graph along the
Yep.
x-axis and kind of go.
Then it would be that same curve, yes.
The pseudo-chlorophyll.
Yeah.
And then you plot that, okay.
Yes.
Great, okay.
Yeah. It's really just using the information from this to translate for every chlorophyll step what the ratio of 490 is to 555, and then changing the x-axis for that last ratio calculation.
You don't do an iteration as you get close enough.
Yeah. Yeah. All right, it's lunchtime, so we now have perfect RRS. I'm sure you're all convinced. I'll come back to that as you depart. It's an awesome video, and anybody who's ever seen me talk knows I find a way to incorporate it into anything. But I just want you to see the final scorecard in terms of all of the different information that's outside of what the satellite actually measures that is required to do atmospheric correction. You have ancillary data for almost every step. This is a list of the sources for your references. This is why it's used. But you also have a lot of lookup tables and coefficients, all of which have their wiggles and so forth. So even if ocean color isn't your thing, there is a lot you can contribute to making this stuff better, which will, whether you like it or not, help ocean color. And so since we have perfect RRSs, I will, come on you. Go. Oh, son of a bitch. I have it. Stay tuned.
While Jeremy's looking for that, I'll just make one other point here, that in a lot of these things, you might be able to do it better because somebody has some fancy way of doing things. But I was Googling around. Motifs Aqua collects 10 megabits of data per second.
Yeah.
So 1.4 terabytes a day from one satellite. So whatever they do here has to be done extremely fast, because all the supercomputers NASA owns could not do this image processing if you did everything the very best way it can possibly be done. So there's a lot of things here where, yeah, you might in principle be able to do something better, but in practice it takes 10 times too long. So you do something that's as good as you can within the time constraint that I have to process 1.4 terabytes of Motifs data every day, and then same thing for beer, same thing for all the other instruments. It's a huge computational constraint on whatever algorithms you use here.
Yeah. And for Motifs and CWIFs, from the moment of collection to the moment it's collection by the satellite to the moment it's on the website, in some cases we can do 3 hours, which is amazing. So, okay, CWIF's biosphere. This is the 10-year anniversary biosphere. Chlorophyll ebbing and flowing in the water. Hot means high, cool means low. And this is NDVI, so arid versus lush regions on land. But I love this image. That's cool. I show it all the time. But, you know, you can see the heartbeat of the Earth. All right, and it's 5 past lunch. So, yeah.